Alright, let's get a G-invariant Hermitian inner product. So, Hermitian inner product means all that stuff up there. So before we get a Hermitian inner product, before we get a G-invariant Hermitian inner product, let's first get a Hermitian inner product. Alright, so we're gonna let Vi from 1 to n be a basis for V. Define an a function given by this thingy, which will end up being an inner product, on Vi direct sum with Vi by if you take Vi inner product with Vj, this is delta ij. So it's going to be 1 if I equals j and 0 otherwise. Extend this to all of V cross V by, let's see here, sum I, AI, Vi, sum j, bj, vj, because these are what arbitrary elements of V look like, linear combinations of the VI's. Okay, so we're going to define this to be sum over I and sum over j, AI, bj, complex conjugate of Vi inner product with Vj. But we know what this looks like because we've defined this on Vi and Vj. It's going to be just delta ij. But this is just going to be 1 or 0, and it's going to be 1 precisely when I equals j, and so this is just a sum over all I, ai, bi, because all the other combinations of I and j's are going to yield delta ij equals 0. Okay, so this is how we define this inner product, or this function, on arbitrary elements. And I claim that this is indeed a Hermitian inner product. Okay, so for the first property, so we want to prove that the linearity in the first coordinate, that's what the first bullet point up at the top means. So let's see, we take this inner product thing of z1u1 plus z2u2 w, and here so z1 and z2 are going to be complex numbers, and u1, u2, and w are going to be elements of V, which are linear combinations of Vi. So we're going to call u1 is sum of ai Vi, u2 is sum of bi Vi, and then we'll say that w is the sum of cj Vj. Alright, so now let's go from here. This is just we can, okay, so we're summing over I in both of these, and so we can combine right, so both of these, each of these terms in the first coordinate, each one is going to have corresponding v1, v2, v3, and so if we factor those out, what we're going to get is we're going to get the sum over I of z1ai plus z2bi times vi. And this, of course, again with sum j, cj, vj. And now we know how to combine this element. We know by definition that this is a sum of z1ai plus z2bi and then ci complex conjugate. So this is equal to z1 and then sum I, ai, ci, just distributing it, plus z2 sum I, bi, ci, and then we basically go backwards, and this is going to end up being z1 of, and then sum I, ai, vi, sum j, cj, vj, Then we're going to add z2, and then sum I b I v I, sum j c j v j. It's not a u, that's a v. But then look, this is just z1 u1 w plus z2 u2 w. Okay, so that's the first property. For the second, we want to know that flipping the two will change the sign. So if we've got, let's say we're taking the inner product of w and v, or here, let's write it like this. V, come on, VW is going to be, let's say V is the sum I, AI, VI, and then the W is sum J, BJ, VJ, and so this will become sum I, AI, BI complex conjugate. But then this is, we can flip the BI's and the AI's, but this becomes sum I, we take the complex conjugate over this whole thing, this is BI AI, right? Because here if you distribute this complex conjugate that we have on the whole thing, then the BI's are going to go back to being complex conjugates, and the AI, when you apply complex conjugate twice, you just get back AI. And so this equality holds. But now this we convert back to sum I bi vi, sum j aj vj, this whole thing complex conjugate, so this is vw complex conjugate. Okay, and that's the second property that we want. Then for the third, if we know that some element sum I, AI, vi is not equal to 0, then we know that ak is not equal to 0 for some index k, which will be between 1 and n. So then we can do sort of an estimate, which is awesome because I love doing estimates because I'm more of an analyst. Although this stuff feels, because there's a lot of vector spaces going on here, this feels a little more like functional analysis. So this is alright, I guess. It's not too bad. Sum I, okay, so this is, if you just do the formula, this is sum I AI times AI complex conjugate. But what's that? If you do that, that's just the sum of the norm of AI squared. And certainly if we're summing over all of these, this is going to be great at least that particular AK squared. And since AK is not equal to 0, this is strictly greater than 0. And yeah, that's what you need for... that's what you need to say that the inner product of any non-zero vector with itself is greater than 0. So hence, this is Hermitian inner product. I'll just say HIP. Alright. Now, in general, this is not going to be necessarily a G-intertwining Hermitian inner product, or G-invariant Hermitian inner product, but we can use this to make one. Alright, so define a new map. We're going to make this like this angle-y thingy prime. This is going to go from V cross V to C by, you take V1, V2 inner product prime, and this is going to equal the sum over all G and G of rho G V1 with rho G V2. I claim that this is a G-invariant HIP, Hermitian inner product. That was a little weird. Yeah, my computer does not like longer problems like this, which you know because I mention it in like almost every video, and I'm sure it doesn't get annoying after a while. Um, yeah, I'm trying to see here. Is there like can we, because this is just a is it obvious? Is it completely obvious that this is a Hermitian inner product? I went through like when I wrote this up, I went through the trouble of reproving every single step to prove that this is a Hermitian inner product because this is for a homework assignment and I don't want to lose points because that's not good for my grade. So just to be super explicit, I went through and I was like, yeah, you just do everything else, or like yeah, I did all of the details. Um, but is that really necessary? If you've got a Hermitian inner product and you define a new map, which is a sum of Hermitian inner, well, because you got the rows in here, I guess it's not entirely obvious. You know what? Let's just do it. Why not? Why would we not do it? Let's just go ahead and do it. All right. We first have, and if you don't want to see this, then just don't watch the video, or skip ahead to when we talk about more interesting stuff. So let's see what this is. This is a sum over all g and g. We have rho g z1 v1 plus z2 v2, and then we have rho g w. And then this is going to be the sum over all g and g of, let's see, we're going to have z1 rho g v1 plus z2 rho g v2, then this with w. No, with rho g w. Do I have enough room here? Rho g w. I'll just write that. Okay. And note that these don't have primes in them. Okay. Alright, so now we got this. And let's see here, that previous step is because rho g is a linear map, and so that's just using its linearity. And now we can use, we know that this thing is a Hermitian inner product, and so we can go ahead and write this as, this is going to be equal, well, we can bring the z1 out front, and then we just get, well, okay, fine, I'll write in another step here. So we got the sum of the g1, rho g v1, rho g w, plus z2, rho g v2, rho g w. Okay? But now we can, because we're summing like this, we can break up the sum into two different sums, and then we can bring the z1 and z2 out front. So this is z1, sum over all g and g, of rho g v1, rho g w. Then we're going to add z2, rho g v2, rho g w. Nope, we're missing a sum here. Z2 sum over all g and, let's do that sum over all g and g. I know that looks really bad, but it's just a computation. Okay, so we've got this. So this is equal to z1 times, well, this is just the inner product, or just v1w prime. Then we add z2 v2w prime. Okay, so that's that. For property number 2, the second thing, we take v1 v2 prime, sum over all g and g, rho g v1, rho g v2. Now we're going to flip these. So this is sum over all g and g. When we flip them, we get complex conjugates, and we can bring that complex conjugate outside because sums work nicely. And then this is just v2 v1 prime. Okay. Now for the third, suppose we have some w, which is in z but is or in v but is not 0. This is actually sort of neat because this is the most analytic step of the problem, I think. Okay, so for the third, suppose that this, for all g and g, rho g is, well, it's a linear bijection on v, so it's, in particular, it's injective. So kernel of rho g consists only of the 0 vector, and so rho g w is not equal to 0. Then, so rho g w inner product with itself, this is a Hermitian inner product. So this is going to be equal to some epsilon g, which is strictly greater than 0, because we know that rho wg is non-zero, and that this inner product is a Hermitian inner product. Okay, so now we're going to do our typical analysis trick, which is awesome, and we're going to let epsilon, well, I guess this is more sort of like the type of thing you'd see in like a compactness argument, but or just any place where you find like you get a finite number of bounds, and then you get the best bounds. So you let epsilon be the smallest epsilon g. Then the inner product of w with itself, well, this is going to be the sum over all g and g of rho g w, rho g w. But this is just the sum over all g and g, epsilon g. And now we get to estimate this. This is, each of these epsilon g's is going to be greater than or equal to the sum over all g and g of epsilon g, which is going to be greater than, no, that's the same thing. So we can replace these epsilon g's with epsilon, since epsilon is the minimum. And so, but then this is going to equal the size of g times epsilon, which is certainly greater than 0. So hence, this, I'm just going to say, is hip. It's a Hermitian inner product. I would say it is a hip, but I don't have room for that. And also no one says that. To confirm that this is G invariant, we have rho GV1, rho GV2 prime. This is the sum over all G and G. Well, now here on the inside, well, I guess let's sum over overall S and G. So here we fixed a G, and we fixed V1 and V2 and V. So I guess there's like a whole bunch of quantifiers in this problem that I'm not specifying, just because it will make it shorter to write, and also you can sort of infer what the quantifiers should be based on where things are being placed. Okay, so we're trying to, so we take the sum over all S in G, then, whoa, okay, thank God we're near the end of this problem. So this is going to be the sum, so we have to apply rho S to rho GV1, and then to rho GV2, but since these are representations, we can combine them into the, okay, come on, I really hope I can make it through this video. So this is going to be rho SGV1, rho SGV2. Okay, so the sum over all these things. But if you look at all elements of the form S times G, where S varies over the entire group, that's going to be precisely the entire group. Because if you consider the map given by left translation blah. Left translation yields a set bijection on a group. And so therefore, summing overall S and G of the row SGs, this is precisely the same as summing overall S and G of row S of V1, row S of V2, because you're just reordering the sum. And that's fine here because this is addition. But look, this is just the inner product of V1 and V2 prime. Okay, and so you apply row G to both entries on the inside of this inner product, and you get back the inner product of V1 with V2. And so that means precisely that this inner product is G invariant, because that's how it was defined at the beginning of the problem. Okay, and so we have constructed a G invariant Hermitian inner product, and this completes our proof.